Thank you. Good morning, learners. Good morning, teachers. Let me take this opportunity I think, to welcome you to this session today. I think this is my second session this year, and you must be familiar with my face. If I have to introduce myself again, my name is Mohapi, working as a subject advisor here in Mutao District, and I'm here today to take you through trigonometry. Trig identities, reduction formulae, and together with those identities that involve Pythagoras theorem. You're welcome, be relaxed, and I'm going to give you lots and lots of exercise because I strongly believe that you as learners, you need to practice a lot. And your teachers will always be there to guide you. We are just a week away from the examination, so please, we need to work very hard. Thank you. Let me start with you today in trigonometry. Thank you. Today we're going to try and prepare you for this coming examination, and you know very well that trigonometry is part of paper 2. So like I said earlier when I introduced myself, my name is Mohapi, and I'm working as the subject advisor here in Mutao District. We're going to focus on trigonometry. Thank you. Please take note, learners. Trigonometry is part of paper 2, and it weighs 60 marks out of 150. Remember, paper 2 will be written out of 150, and the exact date will be the 5th of November. On the 5th of November, you will be sitting for trigonometry in paper 2, and remember, this trigonometry will then be weighing 60 out of 150 marks. So it is important that we need to tackle geometry because you cannot afford to lose so many marks. It's part of paper 2, and it carries plus or minus 60 marks in the examination. I've also bring along the formula sheet so that I should be able to see which formulae are applicable in trigonometry. Thank you. You see, in trigonometry, we have those sine rule, as well as the cos rule, and the area rule there. Sine rule, cos rule, area rule, but today I will be focusing on, this is a formula for compound angles. The sine and cos of alpha plus beta is a compound angle, and here sine and cos of alpha minus beta is a compound angle. These formulae appear in the formula sheet. So in case you have forgotten the formula, it is always advisable from time to time to refer back to the diagram sheet so that you can be able to write down the correct formula. We also have a double angle formulae, the cos of 2 alpha, and as you can see, cos 2 alpha can take 3 forms. Cos 2 alpha can be simplified to cos squared alpha minus sine squared alpha. It's a double angle, it's 2 alpha, but here we only have half alpha, and here we also have got alpha. So the cos of 2 alpha can be equated to cos squared alpha minus sine squared alpha. Alternatively, can be equated to 1 minus sine squared alpha, or it can also be equated to 2 cos squared alpha minus 1. I think you are familiar with this. Main intention for me showing you all this is just to remind you of the formulae, and before we can get into the real work, so that at least you'll be able to recall the formulae correctly. This was the double angle for cos 2 alpha, and here we've got the double angle for the sine of 2 alpha, and sine 2 alpha is equal to 2 sine alpha cos alpha. This is the section of the work that I will be focusing mainly on for today. Trigonometry, compound angles, double angles, including the identities. As you can see, identities are not indicated here, and remember we've got those two main fundamental identities. Sine squared alpha plus cos squared alpha is equal to 1, and the second one, tan alpha is equal to sine alpha over cos beta. You must also know that by heart, because as we will be simplifying problems relating to compound and double angles, to a certain extent we will be required to apply those fundamental identities. Tan alpha equals to sine alpha over cos alpha, as well as sine squared alpha plus cos squared alpha being equals to 1. Thank you. Let me carry on then. Reduction formulae. You have to let me remind you a bit about the reduction formulae. And remember, in reduction formulae, that's where we reduce compound angles to acute. In reduction formulae, we reduce compound angles to acute. Thank you. The sine of 180 degrees minus theta, if I were to take you through that, remember, 180 degrees minus theta, according to cast diagram, 180 degrees minus theta is an angle in the second quadrant. And if you use the cast diagram, in the second quadrant, all these other trig ratios are negative except for sine. That's why, if you look here, 180 degrees minus theta, this is an angle in the second quadrant. And in the second quadrant, according to cast diagram, sine will be positive. Do you still remember the cast diagram? I can see some of you still do remember, some don't remember. Let me quickly take you through cast diagram. Thank you. Thank you. Imagine you've got the Cartesian plane, the horizontal axis, the x-axis, and the vertical ones, the y-axis. Remember, a Cartesian plane has got 4 quadrants. The first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. It's a Cartesian plane. Cartesian plane has got 4 quadrants: first quadrant, second quadrant, third quadrant, and fourth quadrant. And in the third quadrant, remember, that's where the angles here ranges between 0 and 90 degrees. All the angles in the first quadrant are greater than 0 but less than 90 degrees. Angles in the second quadrant, they'll then be greater than 90 but less than 180 degrees. Angles in the third quadrant, greater than 180 degrees but less than 270 degrees. And again, the fourth quadrant, angles in this quadrant will then be greater than 270 degrees but less than 360 degrees. Basically, angles in the first quadrant, those are the acute angles. An angle greater than 0 but less than 90 degrees. You know, an acute angle, an angle less than 90 degrees but greater than 0. So in the second quadrant, you know how we name angles in the second quadrant? Because we've got 180 here. We've got to express angles in the second quadrant using an acute angle. Let me say, in this case, can I use theta in this case to denote an acute angle? I'm going to use theta to denote an acute angle. So angles in the second quadrant, this is 180 at this point. So in the second quadrant, angles will be named as 180 degrees minus theta. We express them like that. Once you see 180 degrees minus theta, then you know 180 degrees minus theta is an angle in the second quadrant. Are we still together? Thank you. Check the third quadrant. In the third quadrant, angles in the third quadrant will be expressed as 180 degrees plus theta, where theta represent an acute angle, where theta represent an acute angle. And in the fourth quadrant, we've got 360 degrees minus theta. This is a cast diagram. By cast diagram, you mean cast diagram. You've got C there, you've got A there, you've got S there, you've got T there. What does that mean? Cos. It means in the fourth quadrant, the cos is positive. Remember, the role of the cast diagram is to indicate the positive trig ratios. Let me repeat myself. Cast diagram, its role is to indicate positive trig ratios. The role of the cast diagram is to indicate positive trig ratios. The trig ratios I'm referring to cos, tangent, and sine. So, according to cast diagram, in the fourth quadrant, cos is positive. In the third quadrant, this is the third quadrant, we've got T there, tangent is positive. In the second quadrant, sine is positive. In the first quadrant, we've got A, where A represent all, meaning sine, cos, tan. In the first quadrant, they are all positive. Thank you. What does that mean? Because I indicate, as I said earlier, cast diagram indicate positive trig ratios. It indicates positive trig ratios, meaning that if we look in the fourth quadrant, we only have C, which represent cos. Only cos is positive. What about sine and tangent? It means in the fourth quadrant, sine and tangent are negative. Sine and tan are negative. Look the third quadrant. we only have tangent. What about sine and cos? It means in the third quadrant, sine and cos are negative. And in the second quadrant, we only have sine. Sine is positive. It means tangent and cos. Tangent and cos will then be negative in the second quadrant. Clear? I was only just trying to take you through the cast diagram, so because it is very much important when we discuss the reduction formulae. Thank you. Let's go back to reduction formulae there. Thank you. We're here at the reduction formulae. Like I indicated to you earlier, once we see 180 degrees minus theta, remember theta in this case represent an acute angle. Theta represent an acute angle. So 180 degrees minus theta is a compound angle in the second quadrant. So we normally say in the second quadrant here, 180 degrees minus theta is a compound angle in the second quadrant. So in the second quadrant, what is the sign of sine? You remember the cast diagram. Sine is positive. That's why you got a positive sine theta. If we have to reduce this compound to acute. In reduction formulae, we reduce this compound angle to acute. So 180 degrees minus theta is the same as the sine of theta. 180 degrees, the cos of 180 degrees minus theta. Second quadrant, 180 degrees minus theta. What is the sign of cos? Cos is negative. Therefore, this becomes negative cos theta. The same applies to tangent. The tangent of 180 degrees minus theta is equal to negative the tangent of theta. 180 degrees minus theta is an angle in the second quadrant. So in the second quadrant, only sine is positive. The rest of the other trig ratios becomes negative. That's why, because in the second quadrant, sine is positive, we only have positive sine theta there. The two cos and tan are negative. 180 degrees minus theta, it represents a compound angle in the second quadrant. Thank you. Let's talk about 180 degrees plus theta now. 180 degrees plus theta is a compound angle in the third quadrant. And according to cast diagram, I hope you still remember, according to cast diagram, in the third quadrant, only tangent is positive. That's why if you've got the tangent of 180 degrees plus theta, it becomes tan theta. Because if you have to reduce this compound to acute, the tangent of 180 degrees plus theta will then be equal to the tangent of theta. Remember, cos and sine, in the second quadrant, they are negative. That's why here we've got minus sine theta, even the cos of 180 degrees plus theta is equal to minus the cos of theta. 180 degrees plus is an angle in the third quadrant. It's a compound angle in the third quadrant. And in the third quadrant, it's only tangent that is positive. It's only tangent that is positive. Sine and cos are negative. Thank you. What is this? What you can see at the moment is the reduction formula for 180 degrees minus theta and 180 degrees plus theta. You as a learner, you need to take into consideration. You should know that once you talk of 180 degrees minus theta, it represents an angle in the second quadrant. 180 degrees plus theta, an angle in the third quadrant. So you then have to know the cast diagram. Cast diagram, remember I said the role of the cast diagram is to indicate the positive trig ratios. Those that are not indicated are automatically negative. Thank you. 360 degrees minus theta. That is also a compound angle. But 360 degrees minus theta is a compound angle in the fourth quadrant. 360 degrees minus theta is a compound angle in the fourth quadrant. And if you can remember the cast diagram, in the fourth quadrant, it's only cos that is positive. That's why here, the cos of 360 minus theta gave us positive cos theta. Look at sine. Sine of 360 minus theta, because 360 minus theta represent an angle in the compound angle in the fourth quadrant, and in the fourth quadrant sine is negative. That's why we've got a negative sine theta. The very same thing applies to tangent. Tangent of 360 degrees minus theta. 360 minus theta represent the fourth quadrant, and in the fourth quadrant tangent is negative. That's why we've got negative tan theta. Thank you. Let me round them off again. Cast diagram. I said cast diagram. Its role is to indicate the positive trig ratios. 180 degrees minus theta, it's an angle in the second quadrant. So in the second quadrant, it's only sine that is positive. Cos and tan will then be negative. 180 degrees plus theta, third quadrant. And in the third quadrant, it's only tangent that is positive. Sine and cos are negative. And 360 degrees minus theta is an angle in the fourth quadrant. And in the fourth quadrant, only cos is positive. Sine and tangent are negative. Thank you. 360 degrees plus theta. 360 degrees plus theta, remember a revolution is 360 degrees. So once you say that revolution, 360 degrees plus theta, then it means we are in the first quadrant. 360 degrees plus theta is a compound angle in the first quadrant. So according to cast diagram, remember you've got the letter A in the first quadrant. So it means in the first quadrant, all the trig ratios are positive. That's why we've got the sine of 360 degrees plus theta is equal to the sine of theta. The cos of 360 degrees plus theta is the same as the cosine of theta, and the tangent of 360 degrees plus theta is the same as the tangent of theta. Because as you can see, in the first quadrant, 360 degrees plus theta, first quadrant, all the ratios are positive. 360 minus fourth quadrant. In the fourth quadrant, only cos will be positive. Sine and tangent will then be negative. Look, 180 degrees plus theta. Only tangent will be positive because according to cast diagram, in the third quadrant, tangent is positive. Cos and sine will then be negative. And then 180 degrees minus theta, second quadrant, and in the second quadrant, only sine will be positive. Cos and tangent will then be negative. These are the reduction formulae for 180 degrees minus theta, 180 degrees plus theta, 360 degrees minus theta, and 360 degrees plus theta. Thank you. Let me carry on with the reduction formulae then. Remember, we also have what we call the negative angles. We also have what we call the negative angles. Yes, can you think? Negative angles. What type of angles are those? Okay, remember when measuring an angle in mathematics, we start from the positive x-axis. And positive angles are then measured anti-clockwise. Positive angles are then measured anti-clockwise. Those angles that are measured clockwise are then referred to as negative angles. So basically, negative angles, those are the angles in the fourth quadrant. Remember, theta is an acute. But now this angle is measured in a clockwise direction. Theta is negative. The angle is measured in a clockwise direction. Let me try and illustrate this. Thank you. When talking of the negative angles, this is what I'm trying to explain to you. You've got your Cartesian plane, set of axes, the system of axes, the xy plane, thank you, the origin there. Now if we measure an angle, let's say for instance here is an angle measured in this direction. See, that angle is measured in an anti-clockwise direction. You remember when you've got your clock at the wall there at home, the clock, how it rotates. So this is against the direction of the clock. Hence it is called an anti-clockwise direction. And all angles measured in an anti-clockwise direction. All the angles measured in an anti-clockwise direction are referred to as positive angles. So probably, let's say this angle will probably be 60 degrees or so forth. Let's say this angle is 60 degrees. Positive angles are measured in an anti-clockwise direction. Imagine an angle here in the fourth quadrant. That is an arm P, the terminal arm OP. Then you measure from the x-axis in a clockwise direction. Let's say the magnitude of this angle is 50 degrees. But because it is measured in a clockwise direction, therefore this angle is referred to as a negative angle. The magnitude will be negative 50 degrees. Basically, that negative sign, it indicates the direction in which the angle has been measured. It has been measured in a clockwise direction. Negative angles are measured in a clockwise direction, whereas positive angles are measured in an anti-clockwise direction. So at the moment, we are talking about the negative angles. Remember, I said, sorry for that, I said theta represent an acute angle. Check this. You've got a Cartesian plane, the x-axis, the y-axis. Theta, in this case, theta, we are going to use theta to denote an acute angle. Remember, an acute angle greater than 0 degrees but less than 90 degrees. But now this acute angle, we are going to measure it in a clockwise direction. So it has to be in the fourth. Remember, this is the first quadrant, the second quadrant, the third, and the fourth quadrant. So if you start from here in a clockwise direction, you measure an acute angle, it will lie somewhere in the fourth quadrant. This angle will then be negative theta. So the negative theta is an angle that is in the fourth quadrant. This negative indicates that that angle has been measured in a clockwise direction. So we also need to reduce these negative angles to positive angles, positive acute angles. Theta represents an acute. So negative theta, we have to reduce it to positive acute. I hope you remember. Then let me take you through this presentation. The reduction formulae. There we are. There we are. There we are. Negative angles, like I indicated to you earlier, negative angles are the angles in the fourth quadrant. They are in the fourth quadrant. And remember, in the fourth quadrant, cos is positive. So the cos of negative theta is the same as the cos of theta, because negative angles are in the fourth quadrant. And in the fourth quadrant, it's only cos that is positive. Look at sine. The sine of negative theta will then be equals to negative sine theta. Whatever you see within the brackets here, it's an angle which is in a particular quadrant. So specifically this one, negative theta, is an angle in the fourth quadrant. So in the fourth quadrant, sine is negative. That's why you've got negative sine theta. In the fourth quadrant, cos is positive. That's why you've got cos theta, positive cos theta. In the fourth quadrant again, negative theta represents an angle in the fourth quadrant. So in the fourth quadrant, tangent is negative. That's why we've got negative tan theta. That's how we reduce negative angles to positive acute angles. Remember, in reduction formulae, I said in reduction formulae, we reduce compound angles to acute. Even here, we also reduce the negative angles to positive acute angles. First quadrant, 90 degrees minus theta. That is an angle in the first quadrant. And in the first quadrant, all the trig ratios are positive. So whenever you see an angle, 90 degrees plus, 90 degrees minus, you should always remember that now we'll be talking about the cofunctions. Means sine will change to cos and cos will change to sine. When does it change? Whenever you see 90 degrees minus, 90 degrees plus. I hope you remember that. I know you must have been taught that in grade 11 and even in grade 12. Some of the exercises that you did during the course of the year, they also involved the cofunctions. Sine changes to cos and cos changes to sine. When will we have that? We only have that change if we have 90 degrees minus or 90 degrees plus. Thank you. So cos of 90 degrees minus theta. The original angle here is cos. The original trig ratio here is cos. The cos of 90 degrees minus theta. 90 degrees minus theta is an angle in the first quadrant. And in the first quadrant, cos is positive. But now because it's 90, then cos will change to sine. Look at this one. The sine of 90 degrees minus theta. The original trig ratio is sine. 90 degrees minus theta is an angle in the first quadrant. So in the first quadrant, sine is positive. But it's 90, then sine will change to cos. If you reduce the sine of 90 degrees minus theta, this is equals to the cosine of theta. 90 degrees plus theta. Thank you. This is an angle in the second quadrant. Check the original function. The original function here is cos. We say 90 degrees plus theta is in the second quadrant. And in the second quadrant, what is the sign of cos? Cos is negative. Now you put minus here. But because it's 90, cos will then change to sine. These are the cofunctions. Cofunctions, whenever you see 90 degrees minus or 90 degrees plus, remember cos will change to sine and sine will change to cos. But it is important to focus on the sign of the original trig ratio. Originally we have the cos of 90 degrees plus theta. So the original trig ratio is cos. We say, what is the sign of cos in the second quadrant? In the second quadrant, cos is negative. Then you put this negative here. Then you change cos to sine because you're talking about 90 degrees plus. 90 degrees, sine of 90 degrees plus theta. The original trig ratio here is sine. The original trig ratio here is sine. 90 degrees plus theta is in the second quadrant. And in the second quadrant, sine is positive. That's why you've got positive cos theta. We have to change. Whenever you see 90, remember, sine will change to cos and vice versa, meaning cos will change to sine. These are the reduction formulae of 90 degrees minus and 90 degrees plus. Let me talk about the compound angles. Compound angles, basically, those are the angles expressed in different forms. It's an angle expressed in different forms. Check. For any two angles, A and B, we have the following. This is in the formula sheet. Sine of A plus B is the same as the sine of A, the cos of B, plus the sine of B, the cos of A. In case you don't have to memorize the formula, but remember this formula is there in the formula sheet. The sine of A minus B, sine A cos B minus sine B cos A. Let me carry on with more compound angles. The cos of A minus B, cos A cos B, plus sine A sine B. The cos of A plus B, cos A cos B minus the sine of A sine B. I don't want to focus more on this one because this formulae are given to you in the formula sheet. They appear in the formula sheet. Also remember the fundamental identity. Remember I said we've got two fundamental identities. The first one is here, sine squared A plus cos squared A is equals to 1. What is the other one? Do you remember the other fundamental identity? Yes, that one of the tangent of A will be equal to the sine of A over the cos of A. It's the second fundamental identity. So you should every time, like I said earlier, whenever we are busy with the compound angles, from time to time we'll have to apply those fundamental identities to simplify or to prove trig expressions. Double angles. You imagine if angle A is equal to B. Let's assume angle A is equal to angle B. Then we get the double angle identity. If you've got A plus A will then give you 2A. So a double angle identity for the sine of 2A is 2 sine A, the cos of A. Double angle of the cos of 2A, remember, cos we said can take three forms, and this formulae are in the formula sheet. The cos 2A can be expressed as cos squared A minus sine squared A. Check. Remember this fundamental identity. Sine squared A plus cos squared A is equals to 1. Sine squared A plus cos squared A is equals to 1. So if you make sine squared A the subject of the formula, then it means sine squared A will then be equals to 1 minus cos squared A. So if you substitute this sine squared A here, you substitute by 1 minus cos squared A. What will you get? You've got cos squared A minus, put in brackets, instead of sine squared A, you substitute sine squared A with 1 minus cos squared A. What do you get? Thank you. If you simplify that one, it means you'll get 2 cos squared A minus 1. And this is also another double angle identity for cos. The first double angle identity for cos is cos 2A is equal to cos squared A minus sine squared A. If you use this identity where you substitute sine squared A by 1 minus cos squared A, then you'll end up with cos 2A being equal to 2 cos squared A minus 1. Oh, see the other one again. Remember, we said that fundamental identity. Sin squared A plus cos squared A is equal to 1. If you make the cos squared A the substitute formula, it means here you've got cos squared A. You substitute cos squared A by 1 minus sin squared A. Because according to the fundamental identity, cos squared A is equals to 1 minus sin squared A. So if you substitute cos squared A by 1 minus sin squared A, what do you get? Thank you. Let me show what you get. Therefore, you'll get cos 2AB equals to 1 minus 2 sin squared A. Those are the three double angle identities for cos. Cos 2A can be expressed as cos squared A minus sin squared A, or cos 2A can be expressed as 2 cos squared A minus 1, or cos 2A can also still be expressed as 1 minus 2 sin squared A. Thank you. I just wanted to take you through that because I just want us to do some exercises relating to the application of everything that we have learned here, from reduction formulae, identities, double and compound angles, and you should always remember what we discussed earlier about the cast diagram, 180 degrees plus which quadrant, and so forth. So I'm going to take you through some few examples whereby we try and apply everything that we have learned here thus far. I'm going to put it into practice. Thank you. I've got the following questions that I want us to discuss together. Thank you. There is a question. Thank you. The question states, from one of the previous papers, consider the expression 1 minus cos 2x minus sin x all over the sine of 2x minus cos x. You consider that expression. First question from that expression states, prove that 1 minus cos 2x minus sin x all over the sine of 2x minus cos x is equal to tan x for 4 marks. Prove that for 4 marks. Thank you. Let me take you through it. Remember, every time you prove, you have the expression there. Prove that 1 minus cos 2x minus sin x all over the sine of 2x minus cos x is equal to the tangent of x. When you prove, every time, when you are required to prove, the question states prove, then you have to choose the complicated side. As you can see, this side, this is the left-hand side, and this one is on the right-hand side of the equality sign. This is the equality sign. This one is the right-hand side of the equality sign, and this one is the left-hand side of the equality sign. So you choose the complicated side. So in this case, the complicated side will then be the left-hand side. This will then be the complicated side. Let's simplify the complicated side. You've got 1, here is 1, minus, here is minus. Now we've got the double angle, cos 2x. We've got cos 2x. And remember, cos 2x can be changed in 3 different ways. Cos 2x can be equated to cos squared x minus sin squared x. Or cos 2x can be expressed as 2 cos squared x minus sin x. Or it can also still be expressed as 2 sin squared x minus 1. So which one will be more appropriate in this case? You ask yourself that question. So I normally say, when you come across the problem like this, just leave that one a bit, leave it like that, go to the next term. Let's check the denominator here. We've got sin 2x, and we know if here the sin 2x is the same as 2 sin x, the cos of x, minus the cos of x. So if you look at this one, you've got sine and cos. And from these two terms, denominator, you're focusing on the denominator, you can see that we've got the cos of x there, you also have got the cos of x there. It means you can take out cos as a common factor. And remember, the question states, prove that this is equal to tan x. So ultimately we are looking to an expression to ultimately find the answer as tan x. Our answer must then ultimately be tan x. So how do we change this one? Because you already have sine there, I would then suggest change this one to sine as well. And remember, put in brackets first. The cos of 2x can also be expressed as 1 minus 2 sine squared x, close the brackets, and then minus sine x, minus the sine of x. Thank you. This one seems to be more appropriate, 1 minus 2 sine squared x for cos 2x, because once we remove here, you can see we'll be able to take out sine as a common factor. Thank you. Let's remove the brackets step by step. 1 minus 1 negative multiplication of positive 2 sine squared x. If you multiply throughout by negatives, negative multiply by 1, -1, negative by positive 2 sine x, you've got negative multiply by negative 2 sine squared x, you've got positive 2 sine squared x, minus sine x, all over denominator you still have 2 sine x cos x minus sine x. So if we simplify it further, let's check what we have. We simplify it further. 1 minus 1, 0. What are we left with? If 1 minus 1 is 0, so this one is off now. 0. You are left with what? 2 sine squared x minus sine x. Then you can see there is a common factor there. Let's take out sine x as a common factor. Sine x. If you divide this term by sine x, you've got 2 sine x minus, you divide this one by sine x, 1. You take out a common factor. After taking out a common factor, you divide throughout by that common factor. So in this case, sine x is our common factor. Divide this term by sine x, you've got 2 sine x. Divide this one by sine x, you've got 1. All over, look at the denominator. If you look at the denominator now, it means we also have the common factor. The mistake that I did when writing this one down, remember we have 2 sine x cos x, 2 sine x cos x, minus the mistake that I did here. Instead of, it should be cos x here. I'm sorry for that confusion. We should be having cos x here. From the original, this is cos x minus 2 sine x cos x, 2 sine x cos x. Sorry for that slovenly work. This is the minus. Therefore, look at the denominator. What is our common factor? Our common factor then will then be cos x. You take out a common factor, divide throughout by that common factor. 2 sine x cos x, you divide by this common factor cos x. You are left with 2 sine x. You divide by that, you've got 1. Divide throughout by common factor cos x. So that you've got the common expression 2 sine x minus 1, 2 sine x minus 1. They cancel off. Then if this 1 cancels this one, goes once into once, therefore you are only left with sine x over cos x. And sine x divided by cos x, according to fundamental identity, this will then give you the tangent of x. Then you can see therefore that the left-hand side, this is the left-hand side, we have simplified this left-hand side, is equal to tan x. Check the right-hand side. Originally the question stated this is the right-hand side. So the left-hand side will then be equal to the right-hand side. They are both equals to 10x. For 4 marks, this is how we prove that identity is true. By applying, initially, we've got the double angle, we also have the double angle, and then at the end here, we've got to apply the fundamental identity. Sin x over cos x is the same as tan x. Clear? Interesting. Thank you. I did this one for you. I'm also going to give you some exercise to do on your own. Let's check the next question here. The next question states 8.2.2. The above expression is undefined if the sine of 2x minus cos x equals to 0. Solve this equation in the interval x greater or equals to 0 degrees or an x less or equals to 360 degrees. In this case, this question has been asked in a simplified manner. Because sometimes you can just say, the question can be phrased as, they just give you this expression. This expression can be given to you. Then the question will then be, for which values of x is the identity undefined? For which values of x is this identity undefined? So this identity will be undefined if the denominator can be equal to 0 here. Then that's why we say sin 2x minus cos x is equal to 0. So let's solve this one. In this one, for the above expression is undefined if sine 2x minus cos x is equal to 0. If denominator here can be equal to 0. Solve this equation in that given interval. Let's solve the equation. You've got the sine of 2x minus cos x, which is equal to 0. We need to solve for x there. Sine 2x. You remember, that is a double angle. The formula for double angle for sine 2x will then be 2 sine x cos x. Now, minus the cos of x, which is equals to 0. Then let's take out cos as a common factor. You can see we have got cos there. We also have got cos x. So we need to take out the cos x as a common factor. If you take out cos x as a common factor, then you'll be left with 2 sine x minus 1. Remember what I said earlier. Take out a common factor. After taking out the common factor, you divide throughout by that common factor. So if you divide by cos x here, you'll be left with 2 sine x. You divide by cos x, you've got 1. Then, from our knowledge in algebra, if you've got the cos of x into the 2 sine of x minus 1 is equal to 0. Therefore, it means cos x is equal to 0, or 2 sine x minus 1 is equal to 0. Now we can solve this one. Remember, angle. Solution must be all the angles greater or equal to 0 degrees, but less or equal to 360 degrees. So, you know, on the y-axis, basically on the y-axis, cos is 0. That's why when you solve this one, it will be equal to 90 degrees, or again, x can also be equal to 270 degrees. The cos of 90, 0. The cos of 270 is 0. And the two angles lie within this given interval. That is correct. Thank you. Check this one. We are done solving this one. When you solve this one, we know on the y-axis, cos is 0. So on the y-axis, we've got 90, we've got 270. Those are the two values. This one, when you solve, let's make sine x the subject of the formula. It means the sine of x will then be equal to 1 over 2. Special angles. And then without using a calculator, special angles. And we know very well that according to cast diagram, sine will then be positive in the first and the second quadrant. You're going to have two angles. The first angle will be in the first quadrant, the other one in the second quadrant. And remember, in the second quadrant, how we name angles in the second quadrant? 180 degrees minus. 180 degrees minus. Therefore, let's check. In the first quadrant, sine x equals 1 over 2. Can you determine the value of x for me? In the first quadrant? Yes. Do not use a calculator, please. Yes. Use those right-angled triangles. Therefore, x equals to 30 degrees. Correct. That is an angle in the first quadrant. Now we also need to determine the angle in the second quadrant. 30 degrees is in the first quadrant. Angle in the second quadrant. Remember, in the second quadrant we say 180 degrees minus. So it will be, x will also be equal to 180 degrees minus this 30 degrees. Then x will also be equal to 150 degrees. So if we solve this equation, the first step, double angle, reduce it to 2 sine x cos x, take out a common factor, then it means cos x is equal to 0, or I'm sorry for the harsh voice, it's like I've got a slight flu, I'm sorry for that. Thank you. It means cos x is equal to 0, or 2 sine x minus 1 is equal to 0. If you solve cos x is equal to 0, x will be 90 and x will be 270. This one, 2 sine x minus 1 is equal to 0. Make sine x the subject of the formula. Therefore, sine x is equal to 1 over 2. When you solve it, x is 30 degrees, x is 150 degrees. Remember, how do we arrive at the two values? We say sine second, first and second. So this is an angle in the first quadrant, this one will be in the second quadrant. This is how we solve this whole problem. Thank you. I've been doing the most of the talking, and I've been doing almost every exercise now. From now on, I just want you to do exercises, because I believe mathematics is about practicing. You need to practice. Practice makes perfect. Through practice, you will become perfect in mathematics. So I'm going to give you an exercise to solve. Remember, this exercise I'm going to give you to solve, it requires the application of compound, double, and fundamental identities. Thank you. Here is an exercise. Are you ready? Take out your pens. Thank you. I want you to solve this one for me. Thank you. Solve this one for me, please. Solve this one for me. Simplify as far as possible. Simplify as far as possible. What is there to simplify? Sine squared theta all over the sine of 180 degrees minus theta, the cos of 90 degrees plus theta, plus the tangent of 45 degrees. For 5 marks, let me give you 5 minutes to simplify that one, and then after solving this one, I'll give you the solution later. You'll compare your solution to mine, and then I'll give you 10 minutes break. Solve this one. After solving this one, I'll give you the solution and then show you how we arrive at the solution. After all that, I will then give you a 10 minutes break. And when you come back, please make sure that you've got papers and pens ready, because you are going to do lots and lots of exercises. Thank you. For 4 minutes now, solve that one for me. Thank you. Okay, right. Thank you. Time is up. Time up. Let me try. Have you got it right? Did you get it right? Some of you are still busy. Some of you managed to finish it in time. Remember, time is a key factor. Time is very much important. We cannot take more than 3 or 4 minutes to solve that one. Thank you. Check. Let's check the solution. Simplify as possible. You've got sine squared theta. Sine squared theta all over the sine of 180 degrees minus theta. Sine of 180 degrees minus theta. Remember, we did the reduction formulae and we said 180 degrees minus theta is an angle in the second quadrant. And in the second quadrant, sine is positive. So we reduce it to just sine theta multiply the cos of 90 degrees plus theta. Once you see 90, then we think of the cofunctions. Cos will then change to sine. But before that, 90 degrees plus theta is an angle in the second quadrant. And in the second quadrant, cos is negative. In the second quadrant, cos is negative. That's why I put this negative here. But because we've got 90 there, then cos will change to sine theta. Plus the tangent of 45 degrees. Special triangle for 45 degrees. Therefore, tangent of 45 degrees using that special triangle, 1. The tangent of 45 degrees will then be 1. Now let's simplify it further. We've got sine squared theta all over. Let's multiply. Sine theta multiply by negative sine theta. Yes? Sine theta multiplied by negative sine theta. Then you've got negative sine squared theta plus 1. Next step. Let's check. Sine squared theta over negative sine squared theta plus 1. This is a fundamental identity. You remember, I said every time this problem that requires the application of the reduction formulae to a certain extent will also be required to know the fundamental identities. And you remember this fundamental identity. Let me show you here. Sine squared theta plus cos squared theta is equals to 1. You remember the identity. Sine squared theta plus cos squared theta is equals to 1. If we make cos squared theta the subject of the formula, you make cos squared theta the subject of the formula. It means this is 1, this minus, and you transpose it to the right. It becomes minus sine squared theta. So what does that mean? Whenever we see 1 minus sine squared theta, we are going to substitute it by cos squared theta. And this is the same as 1 minus sine squared theta plus. It's just a matter of rearranging the terms. So minus sine squared theta plus 1 is the same as 1 minus sine squared theta. 1 is positive, 1 is positive, minus sine squared, minus sine squared. It's just a matter of rearranging the terms. So we substitute minus sine squared theta plus 1. We substitute it by cos squared theta. Then you've got sine squared theta all over cos squared theta. Thank you. Now this also leads us to another fundamental identity. Sine divided by cos. Sine over cos, remember that fundamental identity, is equals to the tangent of theta. But because it's sine squared and cos squared, it means theta will also here be squared. Thank you. The question stated, simplify as far as possible. This is how we have simplified this one. This is how we have simplified this one. Did you get it right? Thank you. Maybe for the next minute or so, let me try and show you how marks are distributed. Remember, initially the question was simplify as far as possible. Sine squared theta. We've got to reduce this one. We had to reduce 180 degrees minus. And when you reduce with the correct reduction, you've got a mark for that. The cos of 90 degrees plus theta, you reduce it. If you reduce it correctly, you'll also be allocated a mark for at that point. Tangent of 45 degrees is equals to 1. You'll also be allocated a mark for that. A mark for reducing 180 degrees minus theta to acute angle, a mark for reducing the cos of 90 degrees plus theta, and also a mark for finding the value of the tangent of 45 degrees. Remember, total marks is 5 marks. So 3 marks are allocated there. Another mark will then be allocated for correctly applying this fundamental identity. Cos squared theta is equals to 1 minus sine squared theta. It means you've got minus sine squared theta plus 1. This is the same as cos squared theta. You applied the identity there correctly. And the last mark will then also be allocated for applying another identity correctly again. But in this case, the fundamental identity that is applied is that one of sine divided by cos, which gives you tan. So you've got 1, 2, 3, 4, 5. That's how marks will be distributed in this question. Are you okay? I can see some of you are getting a bit tired. Fine, let me give you 10 minutes break. But immediately you come from break after 10 minutes, make sure that you are well seated and you are ready, because we still have to do some exercises. Please make sure that you've got enough papers. You've got enough papers where you'll be able to write down the solutions. And you must also have your own pens. Do these problems on your own. You make me, I'll come and rectify. And then in case you still don't understand, remember, you can still send an SMS whereby you ask me to explain it even further. On that note, I think you can have a 10 minutes break. Let's meet exactly at 9:05. Thank you.